I spent a couple weeks developing formalism. Originally objections were there were too many figures and not enough formulas. Now I hear only total silence. I have no idea whether anybody understood anything at all. So what I will do is I will apply the formalism as is custom in physics. And there is a very beautiful example of application of theory of dynamical systems or chaotic dynamical systems to foundation of statistical mechanics. This week's topic I call diffusion. Confusion. It's unfair because it's, as you'll see, it's very simple stuff that you will understand. This is not actually the confusing part of the course. So it's really just deterministic diffusion. And what's fascinating about deterministic diffusion, we are used to notion of diffusion of being the essential thing about stochastic processes, the foundation of all stochastic physics. There the idea is you don't know anything, so assume that there is a noise source, usually Gaussian, makes it easier, but there are also theoretical reasons why Gaussians are preferred. And then you go from there and you develop stochastic analysis, Black-Scholes algorithm, all kinds of stuff, do biophysics. But what we'll study here is much closer to the foundations, the way that Boltzmann and Maxwell thought in the 19th century, which is we have the equations of motions for particles. Let's say equations of motion for argon molecules. They're, for all practical purposes, perfect elastic spherical balls. And lots of them jostle together, and out of that comes Maxwell distribution, Boltzmann distributions, Gibbs, and all kinds of beautiful things. And what happens in the process is we lose the information about the original system and we replace it by some statistical parameters called transport coefficients. The one that you know best is called diffusion constant, and it just tells you that if you drop some quantity of ink in water, it will diffuse, it will spread out due to molecular motions. But the trick here is to actually derive transport coefficients from laws of physics. So you start with equations of motions and we'll get a result. We'll get a number out. And the beauty of this theory is that no probability assumptions are ever made. Every step is deterministic. There is no Gaussian showing up anyplace. And actually one of the main things you show is that the deterministic chaos creates diffusion which is not Gaussian. So it's actually a signature of chaotic dynamics.